Okay, so this is the second part of the differentiability handout, pages 3 and 4. And in this one, we're going to be looking at where um, functions might fail to be differentiable. And so there are four main cases that we're going to look at. Now, the first case is actually the one that I listed last year. If a function is not continuous somewhere, then there's no slope at that point. So in this case, we've got a discontinuity at x equals 0. Even though there's a slope on the left side, this slope right here is always 0. And this slope over here, well, actually, let me write it this way. Y on this side is -1, and y on this side is 1, right? So if I said, well, what's the slope on the left side of 0, f prime, on the left side of 0, well, the slope of this thing right here is 0. So it's 0. And if I said, what's the slope on the right side? Well, this slope up here is also 0. And so a lot of students would think that means, oh, well then f prime of 0 must equal 0. Some students might say this, f prime 0 equals 0, which is normally true, except it has to be continuous, right? F prime 0 does not equal 0. And instead, we'd say f prime 0 does not exist because f is not continuous at x equals 0. So continuity is hugely important here. You have to be continuous in order to have a derivative. Okay? And just because you're continuous, you're not guaranteed to have a derivative either, which we'll see in the other three examples. Whoops. Hold on, let me shrink this down. All right, so let's go up to here. F of x equals root x. Now on the side here, I'm going to write, on the left side, this is really the graph of y equals -x. And on the right side, this is the graph of y equals x. So that means on the left side, my slope is -1. And on the right side, my slope is 1. Now the one place where this gets a little ambiguous is at x equals 0. So if we examine around x equals 0, f prime on the left side of 0, just to the left of 0, is -1. And f prime just to the right side of 0 is +1. And since they're different, left-hand derivative does not equal the right-hand derivative, right? But both are finite values. And when they're both finite values, they're both like regular number slopes, but different slopes, then you would call that a corner. Now you got to be a little bit careful. Corner, you're used to corners being kind of like sharp angles. They don't always look quite like that. So if you actually go up to the previous example here we had a finite slope on the left side of 0 and a finite slope on the right side of 2. So even though it looks like this, that's considered a corner too. Right? So let me go back down here. So the formal definition for a corner is the slope on the left and the slope on the right are not equal to each other, but they're both finite. Okay, the next example is the vertical tangent one over here on the right side. Now I'm going to rewrite f of x. Instead of cubic root of x, I'm going to write x to the 1/3. Because if I write it that way, then I know, so I'm going to write it here, f of x equals x to the 1/3. So then I can say, let me shrink this down a little bit. So since f of x equals x to the 1/3, I can use the power rule to say f prime x equals, and then you bring down the power in front, and then you lower the original power by 1, so it's 1/3 minus 1. So 1/3 minus 3/3 is -2/3. And then if I write that in like fractional form, that's like 1 over 3x to the 2/3, which is 1 over 3 times the cubic root of x squared. Excuse me. Okay, so let's look at the left and right side of 0. Right? So to the left side of 0, the derivative is going to be 1 over 3 times the cubic root of just less than 0 squared, which is basically going to be 1 over 3 times a really, really tiny positive number, because I'm squaring the negative and then taking the cubic root of that. So 1 over a tiny positive number goes to infinity. And if you actually look right here, if you could draw a tangent line getting closer and closer and closer to 0, that tangent line is super steep right there. And so it looks like it's going to infinity. And then if we look at the other side, f prime 0 plus, so just on the right side of 0, well, you can kind of tell that's pretty steep too. And that's 1 over 3 cubic root 0 plus squared, which is also going to infinity. So we would say, since the left hand and right hand derivatives are some type of infinity, it could be positive infinity, could be negative infinity, then we get a vertical tangent. Right? Notice it's a straight up and down, just for one moment, right at 0. That's what the tangent line looks like. Okay. So let me shrink this one down a little bit. Okay. So there's one special case of the vertical tangent called the cusp. So let's look at the cusp. And in this one, we're looking at f of x equals x to the 2/3. So if I use the power rule, that means that the derivative is going to be bring the power down in front and then lower it by 1. So if I subtract 3/3 from 2/3, I get negative 1/3. And if I write it in like fractional root type notation, that's 2 over 3 times the cubic root of x. So now if I said, okay, let's look at the left derivative, the left side of 0. Well, that's going to be 2 over 3 cubic root of 0 negative. And cubic roots, you can't take the cubic root of a negative number. So the cubic root of a tiny, tiny negative number is 2 over a tiny negative number. So that goes to negative infinity. And if you look at it right here on this side of the graph, the slope is really steep going downwards. So this slope on this side, m, is close to negative infinity. Over on this side, you can probably guess m is going to be close to infinity. But to verify it, let's look at f prime of 0 on the right side. And so that's 2 over 3 times the cubic root of a tiny positive number, which, yeah, it is positive infinity. So the conditions that you need for a cusp, now notice it's still a negative infinity and a positive infinity, so we meet the criteria for vertical tangent, and right at that point, the tangent line would be vertical. So yeah, it's vertical tangent. But since it's negative infinity and infinity, so here's what we'd write. So 1 of the left hand or right hand derivatives is infinity, and the other is negative infinity. And so then that gives us a cusp. And depending on left side, right side, which one's negative, which one's positive, you can tell if this thing points downwards or upwards. If the first slope is negative infinity, and then the second slope is positive infinity, then you know it's a cusp that actually points downwards like this. But if it had a cusp where first you get a positive infinity slope followed by a negative infinity slope, then you get a cusp that points upwards instead. So the key for a cusp is it's a vertical tangent, but on one side you get a positive infinity, on the other side you get a negative infinity slope. Okay, so then if a function's continuous at a point, does it have to be differentiable? Well, no. Look at the first three examples here. It's continuous at 0 here, but not differentiable. There's no derivative there. Here it's continuous right here, but no derivative right there because you would get infinity, which isn't a real number. Here, same deal. You get infinity, and here it's, well, this one's not continuous, so that doesn't matter. So if a function is continuous at a point, is it necessarily differentiable? No. You could get a corner, a vertical tangent, or a cusp. If a function is differentiable at a point, does it have to be continuous there? Yes. If you're going to be able to get the slope somewhere, then you have to have the graph connected there. So for a function to have a slope at a point, it must be continuous at that point. Okay? So let's do the next problem here. Actually, I'm going to skip this part for now. We'll come back to that later. Let's look at example 5. So we're going to check for continuity first. So it says first determine if the function's differentiable at the point. So we're going to check for continuity. So f of x equals this piecewise function. Is it differentiable at x equals 0? Okay, so first, technically what we should always do, first check for continuity at x equals 0. Because if it's not continuous, then it's not differentiable. Okay, so continuity goes back to the last unit. So we're looking what happens when x goes to 0 from the left, what happens when x goes to 0 from the right, and what's f of 0. And if those three things are equal, then it's continuous. So from the left side of 0, we're using the top function because that tells us what happens when it's just less than 0. So that's going to be 2 minus 2x minus x squared. And at this point, I can just plug 0 straight in, so it's going to be 2. For the other one, its limit as x goes to 0 from the right of 2x plus 2. So that's 2 times 0 plus 2, which is 2. And f of 0 is the second function there when I plug in 0. So that's also 2. So since limit as x goes to 0 from the left of f of x equals the limit as x goes to 0 from the right of f of x equals f of 0, f is continuous at x equals 0. So we have continuity. Okay. So next, check left hand and right hand derivatives at x equals 0. Okay. So let me shrink this down. Oops, lost it again. Okay, so on the left of x equals 0, we know that f of x equals 2 minus 2x minus x squared. And so the derivative of that, now this is using a rule that we haven't really formally talked about, but you take the derivative of each piece. So the derivative of 2 is 0, right? The derivative of negative 2x is negative 2, and the derivative of negative x squared is negative 2x. I'm just using the power rule on each one here. So f prime of x on the left side of 0 is negative 2 minus 2x. So f prime just to the left of 0 is negative 2 times, or minus 2 times 0 from the left, which is negative 2. Okay, so this one right here, left-hand derivative. On the right side of x equals 0, we've got f of x equals 2x plus 2. Well, the derivative of that is always 2. The slope is always 2. So f prime just to the right of 0 is also 2. Well, now you can look at this and say, well, the left-hand derivative and the right-hand derivative aren't equal. So since the left-hand derivative at 0 does not equal the right-hand derivative at 0, f prime at 0 in general does not exist. So f is not differentiable at x equals 0. Okay. And then let's do the last problem here. And it's going to work the same way, except now we're looking at x equals 2. So first, check for continuity at x equals 2. So we're going to look at limit as x goes to 2 from the left of f of x, limit as x goes to 2 from the right of f of x, and f of 2, and see if all three of those guys are equal. And let's see, on the left side of 2 we have to use the top function, so that's 1 over x. So that's going to be 1 over 2 from the left, which is just 1/2. And on the right side, we got to use 4 minus x all over 4. And when I plug in 2, that's 4 minus 2 over 4. 4 minus a little more than 2, but that's really going to be 2/4, which is 1/2 again. And then the equals 2 goes with the top function, so that's 1 over 2, which is also equal to 1/2. So since lim as x goes to 2 from the left of f of x equals limit as x goes to 2 from the right of f of x equals f of 2, f is continuous at x equals 2. So we've got continuity taken care of. So let me shrink this down, and then we'll check the left and right-hand derivatives too. Okay, so next, check left-hand, right-hand derivatives around x equals 0. Or sorry, 2. X equals 2 is where we're looking. Okay, or we can say at, since that's what we've been using. Okay, so on the left of x equals 2, we have that f of x equals 1 over x, which is the same thing as x to the negative 1. So if I use the power rule, I bring that power down in front and then lower it by 1. So this is the same thing as saying f prime x equals negative 1 over x squared. Okay? So then at just to the left of 2, the slope of this function is going to be negative 1 over 4. 2 squared, right? So there's my slope on the left side, left-hand slope. On the right of x equals 2, I've got f of x equals 4 minus x all over 4. Now I'm going to manipulate that just a little bit. That's the same thing as 1 minus 1/4 x. So then if I said, well, what's the derivative of that? Well, the slope in, this is basically mx plus b form, where the slope is always negative 1/4. So, actually, I'm going to get rid of that. So then if I said, okay, well, then what's the slope just to the right of 2? Well, it's always negative 1/4. So now I can say this line, okay, since f prime of 2 from the left, or actually first let me say, since f is continuous at x equals 2, and the derivative on the left side of 2 is the same as the derivative on the right side of 2, and they both equal negative a fourth, then f is differentiable at x equals 2, and f prime of 2 in general is negative 1/4. So the slope just to the left of 2 is negative a fourth, just to the right of 2 is negative a fourth, and it's all connected at 2. So I would say that the slope itself is negative a fourth at 2. Okay, I hope that helps a little bit.